So for the calculation, we're gonna, since the part one, question one only requires us to use the Z transform, only requires us to do the Z transform on the questions given in the question one, part A, part B. And then for the question one, we found out that through the calculation, we found out that the answer for it would be this negative 2z over 3 multiplied with 2z minus 1 minus 4z over 3 multiplied with negative z minus 2, or it can be translated as this: negative z over 3 bracket z minus half, and then minus 4z over 3 bracket z minus 2. So we're going to take a look, and we're going to have to verify our answers using the MATLAB. So we're going to take a look at the code used for the MATLAB. So here, in this case, we are having the equation, which is right over here. This exactly the same equation given from the question. We're going to do the Z transform just like this. It's as simple as that. Just Z trans and Z trans the entire equation, and then we're going to display the output out in a simple mathematical value using the pretty H coding. So the output would be negative 4 over 3 to the power of n. No, this is just the equation, sorry. So the output is going to be negative 4z over 3 bracket z minus 2 minus z over 3 bracket z minus half. So the output is going to be the same as this, as we can see here. Negative z over 3, z minus half, negative 4z over 3 bracket z minus 2. So exactly they're just the same. Now moving on to the next question, we're going to have the half n un minus 1 over 4 a quarter multiplied with 1 over 2 n minus 1 un minus 1. Through the calculation, through the Z transformation method, by following the Z transform pair table, we're going to have the final answer, which is the z over 2 multiplied with z minus 0.5, which is our final output. And then in this case, from this, we're going to basically just going to do the same. We're going to put or write or copy and paste exactly the same equation from the question provided in the laboratory sheet into, and we're going to store it into the H, which is our variable. And then we're going to do the same thing, which is to Z transform the H, the entire equation. And then we're going to print the X, or to show us the X in a plain text format that resembles the typeset mathematics. So through the simulation from the MATLAB, we know that this is our final output, z over 2 bracket z minus half, which is exactly the same as this, z over 2 bracket z minus half.
I present question 2 in this lab sessions. For question 2a, given the z transform is equal to these equations, then we need to determine the impulse response by applying the inverse z transform. First, we need to apply the partial fractions into the equations, which we will get these equations. Since that the equations got the unknown coefficients of a and b, hence we need to use these equations to find the coefficients of a and b. Hence we get a equals to negative 5 and b equals to 7. Therefore the equations is equal to this one. Then by applying the inverse Z transform using the Z transform table, there are 3 possible regions of convergence RLC in this case. Therefore, there are 3 sets of impulse response equations. For case 1, if RLC Z is more than 1, the system is causal. Then the impulse response Hn is equal to this one. Then for case 2, if the RLC Z less than 0.5, the system is anti-causal. Hence, the impulse response Hn is equal to these equations. Lastly, for case 3, if the RLC Z less than 1 and more than 0.5, the system is non-causal. Hence, the impulse response Hn is equal to these equations. Then we do the simulations in MATLAB software. This is the code that we will use to find for our questions. Hn equals to Iz trans H. This is to perform the inverse Z transform of Z plane system H. Then we run the code, and we can see that the Hn is equal to these equations, which is similar in the case 1 in calculation. This is because the MATLAB always assumes the system is causal. Then for questions 2b, the given Z transform is equal to this one. Then we need to determine the impulse response by applying the inverse Z transform. First, by applying the partial fractions, the H is equal to these equations, which we got 4 unknown coefficients, which are A, B, C, and D. Since bracket Z plus 0.5 squared power 2 is a multiple order pole, then we need an extra formula to find the value of B. This is a formula that we will use. Then in this case, the M equal to 2 and I equals to 1. Hence, after we substitute into the formula, then B is equal to 93/1225. To find A, C, and D, we will use the formula same as in questions 2. Hence, we will get A is equal to -1/70, C is equal to -32/25, and D is equal to 108/49. Hence, we will get the Hx is equal to these equations. Then we multiply the numerator and denominator of Z/70 bracket with Z plus 0.5 power 2 with Z power -2, while for the other terms of numerator and denominator with Z power -1, and we get the Hx is equal to these equations. Then we applying the inverse Z transform using the Z transform table. There are 4 possible regions of convergence RC in this case. Therefore, there are 4 sets of impulse response equations. For case 1, if RCZ more than 3, the system is causal. Hence, the impulse response Hn is equal to these equations. Then for case 2, if RCZ less than 3 and more than 2, the system is non-causal. Hence, the equations of impulse response Hn is equal to this one. Then for case 3, if RCZ less than 2 and more than 0.5, the system also is non-causal. Hence, the Hn is equal to these equations. Then for lastly, the case 4, if the RCZ less than 0.5, the system is anti-causal. Hence, the impulse response Hn is equal to these equations. Then we will do the simulations in the MATLAB software. This is the code that we will use to find for questions 2b. By running the code, we can see that the impulse response Hn is equal to these equations, which is similar in the case 1 in calculations, but the answer will slightly different in between simulations and calculation. The MATLAB is always assume the system causal, so that we just get the one equation for impulse response in MATLAB. That's all from me. Thank you.
For the question 3, LTI system is given as here, which is yn minus 3/4 n minus 1 plus 1/8 n minus 2 equal to xn plus 2xn minus 1. To determine the poles and zeros for the system, the n is substituted by z, which is equal to this equation, and we will get the rearrange the equation will obtain this, which is yz over xz equal to 1 plus 2z power minus 1 over 1 minus 3/4 z power minus 1 plus 1/8 z power minus 2. And the finalized answer is this after we multiply with z power of 2 for both numerator and denominator. The zeros we can get from the numerator, which is z equal to 0 and z equal to minus 2. For the poles, we can get from the denominator, which is z minus 1/2 equal to 0, and the answer is z equal to 1/2. And the second pole is z minus 1/4 equal to 0, and we will get the answer z equal to 1/4. So here is the image for the poles and zeros by manually draw, and the poles is located at 0 and -2. 0 is located at 0 and -2 for poles is located at 1/4 and 1/2. For B, the system impulse response is calculated to determine that if it is causal or not. So at the first, we will move the z to the hash z over z to calculate the partial fraction. By applying the partial fraction, we will get the answer a equal to 0, b equal to -9. Hence, we will get an equation as here. And using the mathematical expression, we will get the final answer, which is 10/1 minus 1/2 z power -1 minus 9 over 1 minus 1/4 times z power -1. By applying the inverse z transform using z transform table, we will get the answer n equal to 10/1/2 power of n un minus 9 1/4 power of n un. We can conclude that the given system is causal because the output depends only on present and past value of impulse response. So for all physical systems are causal systems. They respond to input only after the application of input. The different causalities on the system are causal system and non-causal system, and the non-causal system is not physically realizable. For the simulation using MATLAB, the MATLAB code is typed at here, which is CLC, clear all, close all, b equal to 1, 2, a equal to 1, minus 3/4, 1/8, z plan in bracket b, comma a to find the poles and zeros for the LTI system. So here is the figure for the poles and zeros plot. So we can see that the poles is at here 1.5 and the another poles is 1.25, which is same with the calculation method. And for the zeros, we will get 0 and -2, also same as the calculation method before. To obtain the impulse response, we will type the code like this: CLC clear all, close all, sims z hash equal to the equation, and n equal to I z trans, which is mean inverse z transform, and we will get a command window at here, which is the final answer for the impulse response n. So the answer is 10 in bracket 1/2 power of n minus 9 1/4 power of n, which is also same like the calculation method. So that's all from me. Thank you.